Assalamualaikum warahmatullahi wabarakatuh. The ladies and gentlemen, I would like to say thank you for watching our presentation. It's great to see you all. Let me introduce myself and my partner. My name is Rifan Prayoga.
My name is Dimas Agung Putra.
My name is Fuad satriyaji.
We are from program study of mechanical engineering. In this presentation, we will discuss about a hydro generator.
In this animation, we'll look at how a hydro generator works. This is a typical New Zealand hydro station. You can see that the station has a dam, which creates a drop from one water level down to another. From outside the station, we can't see the generators. If we approach though, we can see the power lines or conductors that carry the electricity from the station to the national grid. Each power conductor connects to a turbine-powered generator inside the dam itself. Let's go inside the dam now and look at one hydro generator to see how the power is produced. The water from above the dam flows down through pipes called penstocks. Each penstock has its own head gate at the top to stop water flow for maintenance or during an emergency. At the end of the penstock is the scroll case. This curls around the turbine like a snail shell. It's designed to create a consistent pressure of water entering the turbine from all sides. Inside the scroll case is a set of vanes called the wicket gates. These control how water flows into the turbine. The wicket gates are controlled by an external governor system. This opens and closes them in response to conditions on the national grid. A high load on the system slows the turbine. The governor system reacts by opening the gates further to speed it back up. Conversely, it will narrow the wicket gates in response to low load on the system. Beyond the wicket gates, we can see the turbine blades. The blades are shaped to extract the most possible spin from the moving water. The turbine blades and the shaft connecting them to the generator are called the runner. We will expand this into its parts so we can see them clearly. At the top is the exciter, which gets a small DC power supply from a cable attached to an external controller called the automatic voltage regulator, or the AVR. Below the exciter is the generator. The inside is a rotor turned by the runner. The outside stationary part is the stator. This is made up of a set of 3 coils of copper wire called windings. On the rotor are a number of electromagnets powered by the DC current from the exciter. If these are switched off, the turbine will be able to spin without generating any electricity. The magnet's poles on the outside of the rotor create a separate rotating magnetic field for each magnet. The magnets are lined up so that adjacent poles always have opposite fields to each other, north-south, north-south. As the rotor spins within the stator, each pole's magnetic field acts on the stator's windings. Each time a pole makes one full revolution, one pulse of AC power is generated in the windings and transmitted towards the grid by conductors attached to the stator. Because the stator is connected to the grid, it's important that the pulses are in time with the grid frequency. When the pulses are in time with the grid frequency, we say that the generator is synchronized. System conditions can push the stator's magnetic fields out of sync with the rotor. The difference between the movement of the stator's magnetic field and the rotor's is the torque angle. The rotor has many electromagnets on it, producing a consistent flow of power. The generator produces three-phase power by using different conductors to carry the power generated along different parts of the stator, as shown here. This creates a three-phase alternating current, which is represented by the sine wave.
In this animation, we will look at how a hydro generator works. This is a typical New Zealand hydro station. You can see that the station has a dam, which creates a drop from one level down to other. From outside the station, we cannot see the generator. If we approach to, we can see the power lines or conductor that carry the electricity from the station to the national grid. Each power conductor connects to a turbine-powered generator inside the dam itself. Let's go inside the dam now and look at one hydro generator to see how power is produced. The water from above the dam flows down two pipes called penstock. Each penstock has its own headgate at the top to stop water flow or maintenance or during an emergency. At the end of the penstock is the scroll case. This curves around the turbine like a snail shell. It's designed to create a consistent pressure of water entering the turbine from all sides.
Inside the scroll case is a set of the Venus skillet, the wicket gates. These control how water flow into the turbine. The wicket gates are controlled by an external governor system. This open and close them in response to conditions on the national gear. A high load on the system slows the turbine. The governor system reacts by opening the gates further to speed it back up. Conversely, it will narrow the wicket gate in the response to low load on the system. Beyond the wicket gate, we can see the turbine blades. The blades are sped to extract the most possible spin from the moving water. The turbine blade and the shaft connecting them to the generator are called the runner. We will expand this into its parts so we can see them clearly. At the top is the exciter, which gets a small DC power supply from the cable attached to external controller called the automatic voltage regulator of the AVR. Below the exciter, exciter is the generator. The inside is a rotor, runner by the runner. The outside stationary part is the starter. This is made up of the set of 3 coils of copper wire, called winding. On the rotor are a number of electromagnets powered by DC corner from the exciter. If there is a switch head off, the turbine will be able to spin without generating any electric. The magnet poles on the side on the rotor grid of spiral rotating magnetic field for H.
The magnets are lined up so that adjacent poles always have opposite field to each other, north, south, north, south. As the rotor spins within the stator, each pole's magnetic field acts on the stator windings. Each time a pole makes one full revolution, one pulse of AC power is generated in the winding and transmitted towards the grid by conductors attached to the stator. Because the stator is connected to the grid, it is important that the poles are in time with the grid frequency. When the poles are in time with the grid frequency, we say that the generator is synchronized. The rotor has many electromagnets on it, producing a consistent flow of power. The generator products three parts power by using different conductors to carry the power generated along different parts of the stator as shown here. This creates a three-phase alternating current which is represented by the sine wave. The conclusion, the rotor has many electromagnets on it, producing a consistent flow of power. The generator products three parts power by using different conductors to carry the power generated along different parts of the stator as shown here. The creates a three-phase alternating current which is represented by the sine wave. The conclusion is that the turbine functions to convert potential energy into mechanical energy. The force of falling water that drives the propeller causes the turbine to rotate. Water turbines are mostly like windmills. By replacing the function of push the wind to rotate, the propellers replace by water to turn the turbines, and then this turbine's rotation is connected to the generator.
Okay, thank you for watching this video. See you next time. Wassalamualaikum warahmatullahi wabarakatuh and bye.